So I was working with this Elasticsearch project where I was trying to understand how to use Elasticsearch and using this donor's choice data, which basically is some public giving data. And to load that into Elasticsearch, there's a Python program. And that Python program takes a few hours to run because most of that process is single-threaded. And I wanted to figure out a way to make that data load faster. And so what came out of that was like, hey, what parts of this can I make parallel? Because not all of it could actually be made parallel. The process wasn't really set up for it, and it wasn't really worth the complexity. It basically loads 3 data files, it massages them, it merges them, and then it massages the results. And so you got to look at what parts can be made parallel and which ones can't. And the reason you got to be a little bit careful. So in Python, there's either multi-threading or multiprocessing. Multi-threading only works really if you're I/O bound. If you want to create multiple threads, and most of the time they're spent waiting, that works pretty well. And that's because the Python processor is single-threaded. There's some locking mechanisms inside to keep the state sane. And so you really can't have multiple threaded CPU-bound items because it'll just swap between them. You'll still get 1 core performance. The other way to do this is to use the Python multiprocessing library. In that case, it spins off data from the primary process and feeds it to these other worker processes. But that means you got to know what data you want to pass, and you have to manage the size of that. And then it will return data. There's no shared state between those processes. So you have to know what you're going to send. You have to send everything it needs, or it needs to load it. And then it needs to return back, and then you need to collect the results. So the question is, what parts of this process for loading the data and for massaging it and loading it into Elasticsearch makes sense to make parallel? So I didn't think it made sense completely because, like I said, you got these 3 data sets you load, you massage them, then you merge them, and then you have a resulting data set, and then you've got more operations to do. So the code loads 3 data files. And I thought, of course, immediately, load the 3 data files in parallel. And it turned out that one of the data files is like about 3 times larger than the other 2 put together. So if I make it parallel, that means I only get like a 25% performance improvement because I can take those 2 smaller files and make their wall time essentially be 0 because they'll both finish before the larger file. So when I played with that, that was really disturbing. I mean, for only 25%, I'm not going to add that complexity. In my case, I wanted like to get 75%. If I was on a 1 core and it took a minute, 8 minutes, and I did 8 cores, I wanted it to be like in a minute and a half, right? So I didn't expect to get n times for however many cores I applied, but I wanted like 75% of that. And I know that because there's overhead in copying the data, bringing it back, merging it together. None of that I would have had if I didn't run it in parallel. So loading the files turned out to be a horrible, not much of a win. The next one I looked at, we had this thing here where for each of these values, we iterate across this thing. And we do this really big operation. So basically, we're going to concat all the resources in one of these iterations and merge them together. And it turns out that each one of these takes like 100 seconds. There's like 8 columns. And if you look at it, that column's data gets concatenated, but just separately from all the other columns. So it looked like a candidate for optimization. The operation takes 900 seconds for the 8 iterations. If I use 8 processors, I was hoping to get this down to like 200 seconds. So I would give up something, but I would get so much that I would save like 700 seconds. And that's a few minutes, right? So I took this code, you take this code where it iterates across the columns, and basically the result is indexed with the same thing as that the parameters were. And we just do this concat operation, right? So I have this resources that were grouped. We're going to do a do concat on it, and we're going to assign the result. And I got this function isolated up here, so I think I can use that function to actually be called by all the different threads, right? So if we look at what we did here, I created a pool of 10, and it turns out there's this thing called star map. I knew that I had the resources columns values. right? And so that's all the values, all the columns that we're going to have. The star map will take that list, that series, and it will fork off one element in that series to each of the workers in the pool. So that means if I have 8 of these that I was indexing across, and I had at least 8 pool elements, in theory, I can get those 8 to operate in parallel with each other. And what happens is when the star map gets called, basically the result for each one of these gets put in a resultant map with the right key. So what I could do after this thing returns is I get this unified map. So we have the indexes. Star map will split it up. We'll split that series up. Each worker thread gets one of the indexes, runs its operation, returns the result. They're still keyed by that index. And so what I can do is I can then just assign. So what you get back actually is I returned the index. So we pass in the index, and then I return the index, and I return the result of the operation. So I get an array back, a tuple, actually. So I know I can set, the first one is the index, so I know that the result gets assigned by the index that we had actually passed out, and then the actual result is the second element in the tuple, and we're done. So that worked pretty well. The second one of these was a series of atomic operations. So we've got, 6 million rows. And we're going to scan those 6 million rows 1, 2, 3, 4, 5, 6, 7, 8 times. We're actually going to do a date conversion on every element in the data set. And then we're going to do another one. And then we're going to do another one. And then we're going to do another one. So this is kind of interesting. We have 6 million elements in the data set. We're going to do 8 operations against them. The operations, because they're just a string format, they're independent of each other. That means I should be able to take the 6 million rows, divide them up by my 8 cores, and have each of them do 1/8 of the 6 million rows. And I can just bring all the results back and concatenate them, and I end up with the right results. So I take the data set, we split it into 8 parts, we pass it off to the 8 cores, and then we get the results back. So this took 1,450 seconds. The parallel version, I have just created a function with those 8 things that have to happen to each data element. And all I did was split the array by the number of workers we had. So we had 8 threads, 8 workers. I took the data set, which had 6 million rows in it, 6.2 million. I divided it by 8. So I created an array, basically a series of 8 items, each with 6 million divided by 8. So it's like 800,000 a piece. And then basically you call this pool.map. What it'll do is it'll call this date function with this. And because I did pool.map and this data was split into 8 parts, each of the cores, each of the pool workers will actually get told to run due date fix, which is this whole thing, on their 1/8 of the data. And then at the end, we just concatenate all that back, and it looks like it was all done by one processor. That actually knocked it from, what did I say here, 1,450 seconds, and it brought it down in 380 seconds. So we knocked about 70% off of that. We got 70% for a very simple change, and we knocked off over 1,000 seconds in the work. So the last change was actually Elasticsearch itself has a parallel bulk method. So they have a bulk method, helpers.bulk, and they have another method called helpers.parallelBulk. You don't have to do anything. All I could tell it is like how many thread counts I wanted and run parallel bulk instead. And then I just iterate across. So it gets 8 different workers, each get 1/8 of the indexing. And then I just check the status of each of those and see if we're good. So these 3 simple changes knocked 100 minutes off of the load process for these 6 million elements. Now there were other parts in there I just couldn't figure out how to parallelize. Basically what I did is I kind of profiled it and see which sections were the longest. And I went to each one of those and tried to figure out whether those could actually be made parallel. And so in one case, the library took care of it. In another case, we used pool.map And in the other case, we used pools.starMap. These were really simple examples. I hope that maybe they'll help you kind of think about your algorithm. You just got to totally have bounded inputs and a bounded result and make sure that the segments don't have to know each other's data to work. And that's it.